Assalamualaikum warahmatullahi wabarakatuh. Good day, everyone. So I would like to present regarding with the PN junction. Yeah. So we have discussed regarding with the PN junction at the equilibrium state. Yeah. Now, what happened when we apply the bias voltage to the PN junction? One useful feature of a PN junction is that the current flows quite freely in the P to the N direction when the P region has a positive external voltage bias relative to N forward bias and forward current, whereas virtually no current flows when the P is made negative relative to N reverse bias and reverse current. This asymmetry of the current flow makes the PN junction diode very useful as a rectifier. Yeah, as the illustration, uh, if we have a PN junction here, this is P and this is N. When we apply the uh, forward bias, so this is battery, the positive and the negative, positive terminal to the P and the negative terminal to the N. So there is the charge injection, yeah, in the junction here, where the whole injection, yeah, from the P to the N, yeah. On the other hand, there is the injection of electron, yeah, from the N region to the P region. So this is to N, for example, yeah. This is this electron from the N region. So in this case, there will be a current flow, yeah, yeah, in the circuit. If we have a P and N junction and then we apply the reverse bias, yeah, when the positive terminal to the N and the negative terminal to the P, so the excess of electron in the N region will be attracted to the positive terminal of the battery, and then hole from the P region will be attracted to the negative terminal of a battery. Yeah, so there will not flow the current, yeah, in the circuit. So the depletion region will be increased, yeah, and then the electric field, yeah, will be increased here. So in this case, there is no current, yeah, flow, yeah, in the circuit. Yeah. So this PN junction has a function to allow the current or to block the current. Yeah. To allow the current when we apply the reverse forward bias, and to block the current when we apply the reverse bias. Yeah. The illustration is like this one as a rectifier. Yeah. So PN junction, yeah, as a rectifier. Yeah. So to rectify the current. Yeah. So if we have the current, alternating current or alternating voltage, but the output is the only the positive, yeah, current, yeah, will flow in the circuit. Yeah, for example, if we have a alternating current, yeah, here, and we connect to the PN junction, this is P, this is N, yeah, So this is your AC power. Right? So if we have a uh, uh, characteristic of voltage here, this is VIC. The VIC, yeah, alternating current as a sinusoidal, for example, like this. Yeah, the originally of this one of the source. And then what happened with the if we uh, uh, yeah uh, apply the circuit alternating current to the PN junction. So when we apply the forward, when the positive to the P here, if in this case uh, positive to the P, so the will current will flow. Yeah, so this is current. But then when changing to the polarity of the positive, yeah, uh, this is a negative and this is a negative and this is a positive, they will not flow the current. Yeah, so this is the depletion region will be increased and then there will no flow current. Yeah, in the circuit. Yeah, so this is there will be zero. And then again when the forward bias applied, uh, so this current profile of the current will not be in the negative one. So this is always positive. So this is the rectifier. Yeah. So this is a as a diode as a rectifier. So therefore the characteristic of the current will be like this one. Yeah. Like this one. Okay. So always positive. So this is a rectifier, and then we can make smoothly if we have combination, yeah, between the PN junction or several diode, yeah. So then we can make uh, more, yeah, rectify the current, yeah. For example, like this one. So they will we will allow the current flow, yeah, in other phase, yeah, at the time, yeah. So like this one. Yeah, so this is can be when we make the PN junction or this diode, yeah, several diode. There are four diodes, and then we can make the profile of the current will be like this. The output, this is output. Yeah. Yeah. So this diode behave like a rectifier. Okay, let's see, analyze one by one when we apply the forward and we apply the reverse bias. If we initially in the equilibrium without any uh, connecting to the bias voltage, yeah. So the profile is like this one, yeah. So this the depletion region in equilibrium because of the diffusion of a hole to the from the P region to the N region. Yeah, the diffusion will causing the depletion region. Yeah, as well as the diffusion of electron from the N region to the P region. Yeah, and then the depletion region will causing the uh, potential different. Yeah, V zero at equilibrium. Yeah, between the P between the P and N, yeah, type of semiconductor. So in the junction, so we have the different potential of V zero, and then the V zero will causing the electric field in the junction, and then further will causing the mobility of a hole, yeah, from the N at the junction region to the left, and then electron from the region in the P region to the N time. So this is the diffusion, sorry, current caused by the mobility of electron or mobility of hole because of the diffusion hole and electrons. And then this returning back of the electron from the uh, P region to the N region we call as the drift of electron, or vice versa, the drift of holes. Okay, and we have when we apply the forward bias. So when we apply the forward bias, yeah, negative terminal to the N type semiconductor and positive to the P type. What happened? Then the electron will push the electron in the N region, yeah, to the junction of the PN. Yeah. So in this case, they will cause the narrowing of the depletion region. Yeah, and narrowing and reducing the voltage difference, yeah, between P and N. So because of the applying of the forward bias voltage, so then that the voltage, yeah, in the junction becoming V0 minus Vf, yeah, and then causing the reducing the electric field. Yeah, further applying of the forward bias voltage, so there will be the injection of the electron from the N to the P, and the injection of the hole from the P region to the N, and then there is the moving of the hole in the cross in the junction. Yeah, so then the current will flow in the circuit. Yeah, the current flow. Okay, this is the current flow. And then the difference of the voltage is the V0 minus Vf, and then the different energy between the P and N is Q V0 minus V0 minus Vf. Yeah, so this is smaller than Q V0. And then when we apply the reverse bias, when the positive terminal to the N and the negative terminal to the P, causing the electron from the N region will be attracted to the positive terminal. So the depletion region will be wider, yeah, than in the equilibrium. The widening of the depletion region will not allow the electron or hole across the junction. Yeah, and then the different voltage is becoming increase, yeah, larger, uh, is V0 plus V reverse bias. Yeah, so this increase. Yeah, on the other hand, we the different energy between P and N will be bigger. Yeah, so this is the applying of the forward and reverse bias, and causing the increasing the electric field in the junction, yeah, and the different energy or different voltage, yeah, changing in the different voltage, yeah, forwards reducing, and then the reverse increasing the different, yeah. Now, if we plot the VI, yeah, voltage versus current, we can just see, and in the forward bias, yeah, in the forward bias, yeah, like in this illustration, in the forward bias, increasing the V, yeah, will causing the flow of the current, yeah, in the circuit. This is the flow of the current in the circuit, yeah, like this one. On the other hand, when we change the polarity, yeah, and the polarity, yeah, P, this is N, yeah, and the polarity like this one, so there will be no current, yeah, flow, yeah, no current flow, but the only small current, yeah, flow in the cross, hole or electron cross the junction because of the thermal vibration. So this is a current, yeah, small, yeah, small current, because of the thermal, yeah, thermal vibration. Yeah, thermal vibration is caused by the applying the voltage, yeah, and then the heating, yeah, causing the activity of electron. The activity electron will causing the vibration of a atom, yeah, vibration of atom further will causing the uh, excitation of electron from the valence band to the conduction band, and then the small current will flow in the circuit. Yeah, So this is the reverse bias. Yeah. So the current flow in the PN junction is like in this equation. Yeah. Later we derive this is as a diode current. Carrier injection. Carrier injection is very important in order to understand whether the PN junction will allow the electron or allow the flow of hole, yeah, or not, yeah, by applying the voltage, yeah. So initially we have uh, the equilibrium ratio of hole concentration and on each side, yeah. A whole concentration in P region and whole concentration in N region at equilibrium. So we have the value of the ratio is this equation. So last time we have derived this equation in equilibrium state. Yeah. So the minority carrier concentration of each side of P and junction to vary with the applied bias voltage, yeah, because of the variation in the diffusion of carrier across the junction, yeah. Uh, become with this become with a bias on the two sides of the transition region, each forward or reverse bias, yeah. So this uh, after applying the voltage, so the concentration of hole, yeah, and both side, yeah, and the P, yeah, side and the N side will be changing, yeah. So let's see the illustration in this, yeah. So this is a PN junction, yeah. So in the PN junction, we have this one, yeah. P, we have P, we have N, yeah. If we have no any external voltage apply or bias voltage applied, yeah, so then we have the concentration of hole in P and concentration of hole in N equal to the epsilon of Q phi 0, yeah, over KT. Phi 0 is caused by the diffusion of a hole and electron, yeah. So this is for example, yeah. So this is diffusion of hole from P region to the N region. This is hole, and the diffusivity of electron, yeah, from N to the P. So causing this is phi 0, yeah. So there is the potential difference between P to the P N, yeah, yeah. So there is the VP and VN. So this VN minus VP equal V0. Okay. Now, when we apply the voltage, yeah, so they will change, yeah, to the minus XP0 to the minus sorry to the xn 0, yeah. So this is the changing, yeah. uh, we have a p yeah, minus xp0 and p xn0, yeah. So they will be change, yeah, when we apply the voltage, when we apply the voltage, for example, when we apply the voltage, they will be changing this one, the concentration of hole. So then the concentration of hole P uh, minus XP0 over P x and 0 equal E, yeah, so Q P0 minus V, yeah, over KT. See now the changing of the concentration of holes in the P region and concentration of hole in the N region, yeah, until this one, yeah. So if we see here, for example, yeah, the concentration of hole in the P region is this one, yeah, and then when the changing, so concentration of a hole and after applying the phi, so becoming this one, yeah, because of the changing of the minus xp0. Okay, so becoming this one. So there are two component of a p ratio of p over pn in this equation, so that we can rearrange this one, yeah, becoming, yeah, p minus xp0 over p xn0 uh, equal to the, yeah, so we adopt this one, yeah, p over pn, yeah, because we have the component v0 here, yeah, the epsilon, uh, epsilon q p0, sorry, q p qp over kt, right? Yeah, and let's see further. Uh, yeah, write again p minus xp0 over p xn0 uh, equal to p over pn, yeah, epsilon q p over kt. Uh, so this is the for the equation, and then we can rearrange, yeah, if we uh, sorry, this one uh, V is negative, yeah. So this is we have a negative V, yeah. So then becoming minus QV0, yeah. This is V minus, okay. And then we can rearrange, yeah. If we move the epsilon, uh, yeah, e power minus qv over kt, so to the left, so we have q e power p over kt equal to the p x n0 over p minus x p0, yeah, uh, p over p n, okay. So uh, we can see here, yeah, we have a concentration of hole at p region and concentration of p uh, at after applying the voltage, yeah, p minus xp0. So this is the we can illustrate like this one, yeah. If we have here the changing of concentration of holes, and this is a junction, yeah, and then this we have xp0 minus xp0, yeah. This is a p a pp, yeah, and then we have uh, this is p n, and then x and 0, yeah, after applying the voltage. So this is the changing here, change to that one, yeah, from the pp to the pp minus xp0, yeah. See here the concentration of holes, yeah, in the p region before, yeah, in the equilibrium state to the increasing the phi, yeah. So we have yeah, for example p, yeah, and then p minus xp0. Okay, so see here now, consideration of p uh, in equilibrium and consideration p at the minus xp0. Yeah, so this is the changing of concentration of p is not significant. So this is almost same. Yeah. On the other hand, we can see that p over p minus xp0 equal 1. Yeah. So there is no changing. Yeah. Because this is the number is much, but the changing is small. So then the concentration of before and after applying a voltage is almost same. Yeah. It will be different if we see the concentration of hole, yeah, in the end region before and after applying the voltage, yeah, whether the reverse or forward bias. So in this case, this very there is the significant difference. Yeah. So this is the uh, 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 for example, yeah, uh, concentration of hole after, yeah, after apply the voltage, yeah, and then the before the voltage applied. So this is a yeah, can be more than one. Yeah, more than one. Okay, this can be understood. Yeah, this is a whole here is small. Yeah, the small amount. So uh, 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 the small changing will significantly different. Yeah. Like this, the illustration. For example, uh, PP, yeah, before is about for example, yeah, for example, 1990, for example, yeah, yeah, PP, yeah, because the 10 is moving to the end region, for example, yeah. So this is a P, this is a equal 10, for example, yeah, because moving to the end region. And then here uh, 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 P, yeah, minus xp0, yeah, becoming, for example, 195, for example, and then the 5 moving here. So then the this is just 15, for example. So then we can see p or px n 0 or pn equal to the uh, equal to 1.5. Yeah, 15 over 10, right? But here equal to the see 1990 over 1985. Yeah, so this is equal one. See the difference. Yeah, so in this case we can yeah, we can remove pp and p minus xpj. Yeah, and then we can have where the p x n 0 over p n, yeah, equal to a q v over kt. Yeah? So this is the constant the significant difference, yeah, between the p concentration of hole after at end region after applying the voltage and at equilibrium, yeah, before the applying the external voltage. Yeah, so there will be dependence of the v, yeah, of course with the temperature and the constant of the Boltzmann. So this is the uh, equation that we can get, yeah, from the applying the voltage. It can be positive, can be negative. Okay, let's see further the analysis. So we have this one, yeah, just now, uh, concentration of hole after applying the voltage and concentration of hole before applying the external voltage with forward bias suggests a greatly increased minority carrier hole concentration at the edge of the transition region on the N side than was the case at equilibrium. Yeah, so In this case, the concentration of hole, after is bigger than the before. So then the concentration of hole is bigger to the concentration of hole before applying the voltage, or at equilibrium. So this is the forward bias. When conversely, the hole concentration under reverse bias or phi negative is reduced below the equilibrium value. So the hole concentration will be reduced, will be less than Pn. So this is, can be understood. The exponential increase of hole concentration at Xn0 with the forward bias is example of the minority carrier injection. So this is the minority carrier injection. So we have P before, after applying the voltage, and before applying the voltage. So there is the minority carrier injection is the difference, delta P, equal in N, sorry, delta P, is the P X N0 minus P N. So this is the minority carrier injection. Negative carrier or positive carrier from the P to the N, or negative carrier from the N to the P. Okay, and then we can have uh, delta Pn. Delta Pn is the excess of hole concentration. Yeah, P xn0 minus Pn, and then we can get this one. And similarly, we can have the excess of electron in P region. In P region is a N minus xp0 minus Np. Concentration of electron in the P region. At the Pn junction region. And then we can get this equation for the excess of electron in the P region. Okay, so if we see the concentration of holes in N region, can be illustrated in this figure. When we have a P-N junction and the depletion region, where the edge of the depletion region in the N region is in this, in this xn0. This is xn0, and then this is the highest concentration of hole, in N region, in this region. So this is because of the applying the voltage, the forward bias voltage. So then we can have the Pn, in equilibrium, plus delta Pn. So this is this is this is delta Pn. Okay, and the concentration of uh, hole will be reducing, when the away from the edge of the depletion region. So this is in this case already, for example, this is Pn, in this region, or more right is the Pn. But in this region, so the concentration of hole dependence of the degradation of the holes. On the other hand, we can have a concentration of electron and the P region, in the junction region here. The highest is the at of the region, junction region here is Np plus delta Np. And then reducing with the away from the at the junction region. So this is maybe here already the Np. Okay. So since this is two this diffusion of a hole and electron, all electron to the left, and then the hole to the right. Yeah. So this the total of uh, uh, the flow here, the flow of a hole and the flow of electron, yeah, in this equation, the whole diffusion current at any point at this is the for the whole diffusion, at any yeah uh, diffusion current at any point here, at the xn, in the xn region, from 0 to this one. This is a xn region is this one, dependence of the diffusivity, and then uh, the uh, diffusivity and the depletion, depletion, of the whole, in the end region, and then we can have further that uh, the current flow of the holes, in the end region, dependence on the diffusivity of hole and the whole diffusion length LP. So this is the uh, uh, whole current, in the end region. On the other hand, we can same same consideration, so we can get the current of electron, in the p region. So can have this way, hole in the n region, this equation. So then we can have a total diode current as uh, the summation of the hole current and the electron current, uh, so this is the we can have a so-called the total diode current I, dependence of the IP and the IN. Yeah? Then we can have this equation, and then the last we can have this equation. So I is equal I zero multiplied by the EQV over KT minus one. So that is that we have just now. The diode current. Okay, and now see about the illustration of the reverse bias breakdown. Yeah, we have found that the PN junction bias in the reverse direction exhibit small because of the thermal vibration, essentially voltage independent saturation current. This is true until a critical reverse bias is reached. Critical bias here, this point, for which reverse breakdown occurs. So this is the will be reverse breakdown. Yeah. So there are two kind of reverse breakdown. This is Zener effect, the operative at low voltage up to the few volt reverse bias, and then the second one breakdown at the higher voltage, where the mechanism so-called the avalanche breakdown. Yeah. So the illustration, the Zener breakdown is like this one. Yeah. If we have in equilibrium, in equilibrium between P and N semiconductor, we join together. So this is illustration. So we have the Fermi level here at the middle, and then when we apply the reverse bias, so the voltage difference between the P and N will be higher, and then will be make the closing, between the valence band and the conduction band, and then allowing the jumping of electron from the valence band to the uh, conduction band. Why this happen? Because the vibration of atom, and then we are causing the absorption of the energy, the electron from the valence band, and then promoting to the conduction band, and then we have so-called the Zener breakdown. Zener breakdown here. Yeah. Uh, so we can see here the the different, energy band gap between the conduction band and the valence band is bigger, initially, and the equilibrium. But when we increase the reverse breakdown voltage, then we'll be closer, will be closing the uh, band gap, between the valence band to the conduction band, and then can have electron, promoting from the valence to the conduction band, and then the breakdown may occur. Okay, and then in the advalent process, so further ionization of the uh, 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 material, whether at the P or N semiconductor. So this is the same, the ionization or the promotion of the electron from the valence band can happen, in both sides. So then the uh, uh, electron in the conduction band will move to the left and to the positive terminal of the uh, battery, and then the hole to the negative terminal of battery. So that there will be there is the moving, or there is the diffusion of the electron and hole across the junction. So the meaning that there is a current flow. So but this is happen for the very huge number of the electron. So then we can have the avalanche process, breakdown. So this phenomena can cause the PN junction breakdown or damage, or burn because of the avalanche breakdown process. Yeah. Okay, thank you for your attention for the today PN junction. By applying the voltage and the external voltage, so then we can have a reverse or forward bias voltage. Okay, so thank you for your attention. So I close this class, and then see you later, for the next topic. Assalamualaikum warahmatullahi wabarakatuh.